Hidden beneath a soft surface are materials engineered to behave like living tissue. Memory foam looks simple, but it is an orchestra of chemistry and precision. Over decades, chemists turned a two-part polyurethane reaction into a viscoelastic material that flows under heat, then slowly recovers. That behavior depends on density, cell structure, and cross-link density. In manufacturing terms, we chase tolerances measured in 3 pounds per cubic foot increments and timing controlled to the second. The challenge is impossible on paper. Create millions of closed and open cells, each a few tens to hundreds of micrometers across, that compress, dissipate energy, and rebound predictably for years. This chapter maps the object, the comfort layer, the support core, the casing, and the seam where chemistry meets human touch. We will follow raw chemicals through violent mixing to gentle shaping and then to relentless testing. Expect heat, pressure, and microscale architecture. Why such rigor? A mattress must support a human body across thousands of cycles without permanent sag while meeting safety and environmental rules. Over the next chapters, we trace the path from petroleum-derived precursors to the slow, deliberate creep that gives memory foam its name, a blend of chemistry, mechanics, and industrial choreography. The journey begins with two industrial liquids, polyols and diisocyanates. Both start from petrochemicals, hydrocarbons cracked and reformed into functional building blocks. Polyols bring long molecular chains that give foam elasticity. Diisocyanates, often MDI, deliver reactive sites that link chains into a network. Additives are tiny but decisive. Catalysts at under 3% by weight, silicone surfactants at parts per thousand, water as a chemical blowing agent measured in tenths of a percent, flame retardants and stabilizers. Each batch is a recipe. A higher polyol viscosity and a higher isocyanate index increase cross-linking, producing slower rebound and deeper contouring, what consumers call memory. Density targets are set in pounds per cubic foot, 3, 4, or 6 pounds per cubic foot, because density controls support and durability. Suppliers deliver drums and IBC tanks to the plant floor. Tanks are temperature controlled to keep viscosity stable, typically in the 40s to 60s Fahrenheit range. Logistics matter. Moisture in the feedstock ruins foam structure, so raw materials are filtered, preheated, and measured with precision metering pumps. Transformation begins here, from common petrochemicals into a carefully balanced reactive mixture that will expand into foam in minutes. Every pint must be right, or the foam will fail at the molecular level. Mixing is where chemistry becomes geometry. On the floor, metering pumps feed precise ratios into high-shear mixers or impingement heads. The two streams collide at high velocity, often 1 to 3,000 revolutions per minute in rotor-stator mixers, atomizing liquids and creating a uniform premix in milliseconds. This is critical. Uneven mix yields weak cells, irregular density, and visible defects. Catalysts start the clock. Water reacts with isocyanate to generate carbon dioxide gas, the blowing agent, and the polymer network forms at the same time. The process has stages. Cream time, the first seconds when viscosity rises. Rise time, when bubbles expand into foam. Tack-free time, when the surface skins over. Typical rise and tack windows are tight, 30 to 90 seconds to rise, a few minutes to tack-free, so downstream equipment must be synchronized. Operators monitor temperatures, mix ratio, and batch weight with inline sensors. Small adjustments, fractional changes in catalyst concentration or surfactant level, shift cell size from tens to hundreds of micrometers, changing firmness and heat conduction. This chapter reveals the violent, beautiful moment when liquid chemistry becomes a porous solid, and why precision makes the difference between luxury comfort and a lumpy disaster. Foaming is sculpted chaos. Gas bubbles produced by the chemical reaction create the cellular skeleton. Control the bubble size and you control firmness, thermal conductivity, and recovery speed. Surfactants stabilize the cell walls, keeping bubbles intact while polymer chains set. If the formulation favors open cells, air moves through the foam, improving breathability. Closed cells trap gas, increasing buoyancy. Engineers measure cell size distribution with microscopes. Cells commonly span tens to hundreds of micrometers. Pouring techniques matter. Slab stock lines pour a continuous curtain into a trough where the foam rises in a steady river. Molded lines inject measured charge into a cavity where expansion is constrained, producing dense, shape-accurate parts like pillows or seat cores. Pour rates, line speed, and knife height are tuned to keep thickness uniform to fractions of an inch. The foaming exotherm releases heat. Operators allow the slab to travel through cooling tunnels or ambient staging to equalize temperature. Too hot and cells collapse. Too cold and cure is incomplete. This chapter shows how foam manufacturers tame bubbling reactions into predictable sheets of engineered air, layer by layer. Curing fixes chemistry into structure. After rise, foam moves to conditioning ovens or staging rooms to complete polymerization and to drive off volatile byproducts. Typical conditioning spans hours to days depending on density and thickness, but initial demold windows are measured in minutes, 20 to 60 minutes for molded parts. Temperature control is critical. Many plants hold slabs at about 110 to 140 degrees Fahrenheit to accelerate cure without degrading surfactants. During cure, crosslinks form and chains lock into the viscoelastic network that gives memory foam its slow recovery. Manufacturers often perform thermal aging or vacuum flashing to reduce volatile organic compounds, off-gassing that consumers can smell. Sealing and post-cure can lower VOCs by 50% or more. Density stabilizes during this phase. Measured in pounds per cubic foot, it predicts long-term sag resistance. Dimensional tolerances are checked with lasers, and moisture content is logged. This chapter highlights why time and controlled heat are less about drying and more about locking in molecular architecture. Get curing wrong, and the foam will either crumble or permanently compress under load. Shaping separates commodity foam from engineered comfort. Two dominant paths produce different product classes. Slab stock lines cut continuous sheets, large slabs that will be sliced, convoluted, and laminated. Molded foam is poured into a closed cavity and cured to final shape, used for contoured pillows and dense support cores. Cutting uses bandsaws, CNC routers, and water jet routers adapted for soft materials. For slab stock, multi-blade gang saws slice the block into mattress layers with tolerances of a few millimeters. CNC machines route channels and perforations for airflow. Knife speed and spindle tower are tuned to avoid melting or fraying. Molded foam demands precise charge weights and venting, so expansion fills the cavity uniformly. Vent pores in molds manage trapped air. For convoluted egg crate surfaces, cutting knives travel in synchronized patterns to create peaks and valleys measured in fractions of an inch. Each shaping step changes surface area and stiffness. Engineers map stress distribution to choose where to place firmer cores or softer comfort layers. This chapter shows how brute force cutting and delicate molding produce the exact feel consumers expect. Comfort is more than softness. Surface engineering manages heat, airflow, and moisture. Memory foam is naturally insulating, so designers add perforations, channels, and open cell formulations to move air and dissipate heat. Engineers use numerical models to place cuts and tunnels that reduce thermal buildup under the human body. Perforation diameters are often a few millimeters and drilled in precise patterns, aligned with pressure hotspots like shoulders and hips. Gel infusions and phase change materials can be blended into the polymer or applied as microparticles to increase heat capacity. Another approach is to create hybrid stocks, a breathable latex or high airflow foam beneath a viscoelastic layer. Surface finishes include knitted covers with cooling yarns and quilting for airflow. Each modification affects compression behavior. Adding channels softens stiffness locally, changing how forces redistribute. Testing uses thermal imaging and contact thermometry to measure skin surface temperature changes in degrees Fahrenheit. This chapter reveals how microscopic changes in surface topology and material composition yield perceptible drops in heat and improved sleep comfort. Assembly turns engineered layers into a sleeping system. Automated lamination tables align comfort layers, transition foams, and support cores to within millimeters. Adhesives are applied with bead guns or roll coaters, pressure-sensitive or hot melt glues chosen to avoid chemical interaction with the foam. Heat presses bond layers and fabric covers seal the stack. For zoned mattresses, CNC-guided placement aligns firmer inserts and channels to anatomical maps. Edge supports often use higher-density rails glued or mechanically fastened to the core. Stitch and tuft operations knit the cover to maintain layer placement, while sergers finish seams for durability. Packaging can be dramatic. Many mattress manufacturers compress, roll, and vacuum seal products to shrink them into boxes. Compression requires calculated strain. Folding and rolling parameters are validated to prevent cell rupture and to ensure recovery time remains within specification. Robotics and PLC controls choreograph conveyors, adhesive dispensers, and presses to keep cycle times low while holding tight tolerances. This chapter reveals the marriage of soft materials and industrial automation required to make a consistent product at scale. Quality control is ruthless. Memory foam must survive thousands of sleep cycles, resist permanent set, and meet safety standards. Fatigue testing machines apply cyclic loads, thousands to hundreds of thousands of cycles, while sensors measure compression set and resilience. Indentation force deflection, or IFE, quantifies firmness in pounds at 25% indentation. Typical memory foams test between 8 to 30 pounds depending on comfort level. Recovery time is measured in seconds, how long until the foam returns to 90% of its height. Thermal aging chambers expose samples to elevated temperatures to predict long-term behavior. Flammability tests follow regional standards. For the U.S., manufacturers reference California TB 117201-301 performance pathways and use barrier materials or compliant additives. Off-gassing is measured in controlled chambers to quantify VOC emissions over time. Any batch that fails tolerance for density, IFD, or recovery is recycled or reprocessed, cut into carpet underlay or automotive insulation. This chapter visits the labs where instruments, jigs, and relentless protocols separate reliable products from rejects. The goal? Guarantee comfort, safety, and years of predictable performance. The final act is packaging and delivery, but the engineering story continues. Mattresses are vacuum compressed and rolled into boxes, which reduces transport volume by up to 80%. Packaging design must balance protection with breathable materials to allow residual gases to escape. At the retail or home stage, the foam decompresses over hours to days, completing slow recovery. Sustainability is now central. Manufacturers explore bio-based polyols derived from soy or recycled carbon streams, and physical blowing agents like water or CO2 replace older chlorofluorocarbons. End-of-life plans include recycling into carpet padding, underlayment, or energy recovery. Performance is felt in tiny details. A foam that softens at body temperature, about 95 degrees Fahrenheit, contours to relieve pressure points at the shoulders and hips while returning slowly to support posture. The final test is human, comfort over days, months, and years. The factory output becomes a nightly interaction between engineered microstructure and living tissue. Memory foam stands at the intersection of polymer chemistry, precision manufacturing, and human ergonomics, a once space-age material now tucked under millions of sleepers every night. I hope this deep dive gave you a new perspective on the strategies and the relentless mindset behind these global icons. If you enjoy deconstructing business empires and tech legends in this Tech Archive style, make sure to hit that subscribe button and turn on all notifications. That way, you will never miss a new blueprint of history. For those of you ready to explore more boardroom coups and technological breakthroughs, I have handpicked 2 videos for you right here on the screen. Click one to keep watching. I will see you in the next one. Thanks for watching.